Thanks. So welcome everyone to this new LIP seminar. Today our speaker is Tahereh Niknejad. She will talk about precision timing with the CMS MTD barrel timing layer for HL-LHC. Tahereh started to work at LIP in 2013. She did her PhD, mainly work on the development of detector modules for the position emission tomography and development of a prototype PET system. In 2017, she got her PhD in technological physics engineering at Technico, and since March 2018, she is a postdoc working on the development of the barrel timing layer for the CMS detector. So since her work in CMS, she received in 2019 the CMS Detector Award for her contribution in development of the front-end chip for the barrel timing layer readout, and she was till November 2020 the coordinator of the BLT front-end ASIC. So whenever you want, Tahereh, please go ahead.
Okay, good morning, everyone. Do you hear me well?
Yes, perfectly.
Okay. Today I'm going to present the MIP Timing Detector for this phase 2 upgrade of the CMS for the HL-LHC. So this is the outline of my talk. First, I will talk about the challenges that we are facing at the HL-LHC, which is a pileup. And then I'm going to talk about the detector requirements in the new challenging environment. And then I'm gonna talk about some examples of the performance for the impact on the performance for physics object and physics analysis. And then later I will talk about the CMS MIP timing detector in details, which includes the endcap timing layer and barrel timing layer. And at the end, I will give a summary of the talk. So the focus of the talk will be the barrel timing layer on which the LIP is leading the development of the readout electronics. So LHC during the operation time, it had several runs and several long shutdowns where they increased the luminosity of the beam. And now we are here where the instantaneous luminosity is 210 to the 34 per square centimeter per second for 300 inverse femtobarn. And for the LHC, which would be operating around this time, 2026, the instantaneous luminosity for the nominal scenario is gonna be increased to 5 to 10 to the 34 per square centimeter per second for the integrated luminosity of 3000 inverse femtobarn, which is 10 times higher than the integrated luminosity of the current state. And for the ultimate scenario, this integrated luminosity is going to be increased to 4000 inverse femtobarn. So this is a very challenging environment because the radiation level is much higher and also the pileup level is much higher. So in this luminosity, we are going to have a very high pileup, around 140 to 200 for every bunch crossing, which is 5 times higher vertex density of the present LHC. And also the radiation level is very high, so it's a very high radiation environment. So this will heavily affect the physics event reconstruction and the analysis unless it is mitigated. So in this challenging environment, for the detectors to work properly, to function properly, we need some upgrading. So the main challenge is that the detectors should be radiation hard. We have to try to also mitigate this high pileup. Otherwise, the increasing of the luminosity has no impact. So here on the plot on the left, you see a real-life event with HL-LHC like pileup from the special run in 2016 with individual high-intensity bunches. And as you see here, the pileup is around 100, and you see that the number of tracks is already very overwhelming, but indeed it's going to be double this amount. And on the plot on the right-hand side, you see the line density for the LHC and for the case where we have 140 pileup and for the case where we have 200 pileups. And you see that for the current LHC, the line density peaks around 0.3, and for the case of HL-LHC with 140 pileup, it peaks and 200 pileup, the peak is around 1.9 per millimeter. So the good point is that we have timing. So the vertices in HL-LHC have a distribution in time with 180 picosecond RMS. And the MIP timing detector that is going to be placed right after the tracker allows to tag in the particles with the timing information with the precision of 30 to 50 picosecond. So on in the plot on the right-hand side, you see the distribution of the vertices in the longitudinal coordinate and also in time coordinates, time axis. And the yellow lines are the 3D reconstruction of the vertices. And if there is no timing information, you see that in different Z position, there is high amount of pileup between the events. And the blue dots are the 4D reconstruction of the vertices, and the black ones are the 4D tracks with timing information. And if we use the timing information, we can reduce the level of the pileup to the current HL-LHC situation. So here I'm going to present the effect of the precision timing on the track to primary vertex association. So in the plot on the left, you see the number of the pileup track that are wrongly associated to the primary vertexes as a function of the line density. So the line density of 140 pileup is around 1.2. So it's here, and the line density of 200 pileup is around 1.9, which is here. So the number of the pileup tracks which are wrongly associated to the primary vertex for the case of 200 pileup can reach over 20. And with the use of the MIP timing detector with a precision of 35 to 60, we can reduce it to around 10, which is as a factor of 2, which is very good. And on the plot on the right, you see the number of the pileup tracks which are wrongly associated to the primary vertexes, the distribution of them. So this is the y-axis, the fraction of the primary vertex that have this number of the pileup tracks. And the red curve is what you get with 200 pileup without any timing information. And the green one is what you get when you have the timing information with a precision of 35 picosecond, which you can almost recover the case of the current LHC, which is 600 pileup. So of course, this timing information has a huge impact on the physics object reconstruction, because we are going to reduce the spurious pileups, and the reconstruction of the events is going to be much cleaner. For example, on the plot on the left, you see the efficiency of the isolation of the muon. And if you have no MTD with no timing information, and for the case of the 200 pileup, which is here, so the efficiency is here. And if you have the MTD with the timing information of 40 picosecond, the efficiency comes here. So you gain some 20% gain in the efficiency. Another impact of using the timing information is the possibility to perform the time of flight particle identification. This is very important for the B physics and heavy ions. For example, on the right, you see the 1 over the speed, the inverse of the speed as a function of the momentum. And depending on the mass of the particles, you can have a very good distinction between the protons, cation, and pion. And at the end, using this time information also has some impact on the physics analysis. Many cases have been studied. Among them is the double Higgs production, which is basically the goal of the HL-LHC, because then they can study the properties of the Higgs with large implication of the physics beyond standard models. So on the plot on the left-hand side, you see the signal yield as a function of the Higgs rapidity. And if you use the timing information from the barrel and the end cap, because MIP timing detector, which later I will explain, consists of barrel timing layer and the end cap timing layer. So this signal yield increased by 22% due to the better reconstruction. And here in this table, you see the sensitivity of the double Higgs channel is going to be increased by 20 to 26%, depending on the timing resolution that the MTD can provide us. So if the timing resolution is around 35 picosecond, the gain in the sensitivity is going to be 26%. And if the timing resolution is around 50 picosecond, which is the case for the end of life of the LHC, the gain in the sensitivity is going to be 20%, which is like equivalent to the gain in the integrated luminosity of around 40%. Another, there is also a unique physics opportunity when using the timing information. One of the examples is the heavy stable charged particles. So in this type of analysis, normally people use physicists use the inverse of speed to discriminate between the particles and the background. So here in the red, you see the red plot is what you get from the heavy stable charged particles, the distribution of the heavy stable charged particles, and the one in blue is the background. So if you use the timing information, the resolution of the distribution of the background is going to be better. So this is going to be narrower, and you can have a better discrimination between the particles and the background. So again, going back to the detectors. So for the HL-LHC, because the radiation level is much higher, then we have much higher pileup events. So the different part of the CMS has to be upgraded, including the tracker, the endcap colorimeter, the electromagnetic colorimeter, the muon system, and this MIP timing detector that I'm going to present in details. So what is in common between all these detector part of this, or this CMS part, is that all these detectors should be radiation hard because the radiation level is much higher. And also in most of the cases, the coverage is also going to be increased. In the case of the MIP timing detector, this is a new layer that is going to be added. So there's no upgrade is going to be added indeed to the CMS. Going back to the MIP timing detector, so the MIP timing detector has consists of the barrel timing layer, which is this cylinder that you see here, and the endcap timing layers, which are placed on both ends of the cylinder. So the parallel timing layer is based on the technology of the barrel timing layer is based on the LYSO crystal bars and read on both ends with the silicon PM readout, and it will be placed between the tracker and the ETL, and the coverage is going to be up to 1.45. The inner radius is around 114 centimeter. The length is around 5 meter along the Z, along the beam, and the surface is around 38 square meter, which has 332 kilo channels. And the fluence that we expect at the barrel timing layer is around 2.2 to 10 to the 14 neutron equivalent to per square centimeter. On the other hand, the end caps that are these two discs on both sides of the BTL are based on another technology, silicon with internal gain, or LGAD. So this is because of the radiation level on the end cap is much higher than the BTL. It is 10 times higher, is up to 2 to 10 to 15 neutron equivalent per square centimeter. And the coverage is going to be between 1.6 to 3, and the radius between 315 to 1,200 millimeter. So it's going to be placed on both sides of the barrel timing layer on plus minus 3 millimeter along the Z or along the beam. And the surface is around 14 square meter, and it has 8.5 million channels. So as I said before, this MTD detector is going to be right after the tracker. So in this plot, you see the MTD timeline. This is different stage of the project, both MTD and both barrel timing layer and the endcap timing layer, from the design and the engineering to production, pre-production, towards installation and the commissioning. So, and the TDR, technical design report, is already approved and is also public. You can find it in this link. So the production of the BTL is going to be between 2022 2023, and the installation should be no longer than end of 2023, beginning of 2024, because it's going to be placed inside the tracker support tube, and it should not interfere with the installation of the tracker. So this BTL has a very tight schedule. On the other hand, ETL has more, it has more freedom in the schedule. It can last longer. So the production is going to be between 2023 to 2024, and the installation can be anytime. It can be in 2025 because it's going to be placed on the nose of the endcap calorimeter. So it can be even done after the installation of the endcap calorimeter. So it has more freedom for the installation time. And the commissioning can be, is going to be somewhere around 2026. So as you see in this timeline, BTL has a very tight schedule. It's the last detector actually to be approved and the first to be installed. So it's a very challenging project. So first I give a brief overview of the ETL endcap timing layer, and then later I go into more details for the barrel timing layer. So the endcap timing layer, as I explained before, are two disks that are placed on both ends of the barrel timing layer. On each side, we have two disks, and on each disk support, which are this one, on both sides of them, we have the detectors or the sensors. The sensors are based on the low-GAD avalanche detector or LGAD sensors, and each sensor is arranged in an array of 16 by 32. Each pixel size is 1.3 by 1.3 square millimeter. And then the readout electronics, which they call it ET-ROG, stands for ETL readout chips, is bonded to the LGADs and can handle 16 by 16 pixels. And each channel of this LGAD consists of the preamplifier, discriminator, TDC to digitize the time over time of arrival and time over the threshold measurement. So these LGAD sensors, which they are also being called ultra-fast silicon detectors, they are basically fabricated by adding another additional gain layer. And they are indeed a development that was common between the CMS and the Atlas. And they have moderate internal gain, which is 10 to 20. They have a large signal to noise ratio, and they are very radiation tolerant. So as I explained before, the radiation level for the endcap is very high, is 2 to 10 to the 15, or 20 equivalent to a square centimeter. And it's very important for a detector to be radiation hard. That's why we use this technology. So in the plot on the right, you see the resolution that we get with this sensor as a function of the gain. As you see that as we increase the gain, the jitter decreases. But the total timing resolution flattened around 35 picosecond. And normally we use lower gain for the end of life because of the leakage current, and a bit higher gain for the beginning of life. And including the radiation damage that we may have at the end of life operation of the LHC, the timing resolution that we can get is around 35 picosecond for the beginning of life and 45 picosecond for the end of life, which is very good, and is what we basically is the goal of the MTD. So now going back to the barrel timing layer. Which is this cylinder. So the barrel timing layer is gonna be mounted on an inner surface of the tracker support tube that you see here. On the longitudinal coordinate, we will have 2 trays, and each tray has 6 readout units. And each readout units has 3 by 8 modules, or 24 modules. And each module is what you see here, has 16 crystal bars, LYSO crystal bars that are being read by silicon photomultipliers on both ends, which I will discuss in the next slide in more details. So the Btl Sensor Design. So as I said, each module has 16 crystal bars, and each crystal bar has a dimension of 3 by 3 by 57 cubic millimeter. That are coupled to 2 SiPM pixels on both ends, and the SiPM pixel size are 3 by 3 millimeter, the same size of the cross section of the LYSO bars. So when the charged particles go to the scintillator crystal, they emit many thousands of scintillation light. These scintillation lights eventually exit the crystals and will be collected by the silicon photomultipliers. and then the signal from the silicon photomultiplier is being read by the readout electronics. So why we have two SiPMs on the both ends of the crystal bars is because we can eliminate the impact of the point dependent, so of the charged particles. So if the charged particles deposit energy here, it arrives sooner here and it arrives later here, and if deposit energy here, it arrives sooner here and later here. And if you make an average, the arrival time is more uniform. It's like it will be independent on the interaction position, which I will explain later in another slide. And also the timing resolution can be improved by a factor of square root of 2, which also you will see it later. So, and then there was a huge work R&D effort on to characterize the performance of various crystals, various SiPM. Type of the wrapping between the crystal pieces is very important to wrap the crystals to avoid the shedding light between one crystal to another, and also to avoid escaping light from the crystals. And also the coupling between the crystal and the silicon photomultiplier is very important to have the maximum light collection efficiency from the crystal to the SiPM. So there was a huge testing and testbench campaign to characterize the performance of various wrapping, gluing to improve the performance of the sensors. So here I explain to you how the timing resolution derives actually in BTL sensors. So the timing resolution has many contributions, which is the clock jitter, digitization timing resolution, electronic uncertainty, DCR noise, and photostatistics. Among all these contributions to the time resolution, the dominant factors are the photostatistics, or the number of photons, and the DCR noise. So what is DCR noise? So the silicon photomultipliers are great sensors, but they have some drawbacks. In the high radiation environment, they can be damaged and they can produce some noise that are being called dark current noise, which are thermally generated electron holes, which are like a normal electron holes that are being produced by the incident light from the LYSO. So they appear like a noise. For example, on the right, you see this is an example of the background DCR noise around 100 gigahertz. And the one in blue is the LYSO MIP signal with 6,000 photoelectron that is superimposed with the DCR. So DCR appears like a noise on the rising edge of the signal and can destroy the timing resolution dramatically. So it's important. So one of the challenges, or the main challenges that we have in the development of the sensors and the electronic, is to eliminate this noise and impact of this noise on the timing resolution. And the right on the right-hand side, here you see the timing resolution as a function of the integrated luminosity. So the clock noise is always constant. It has nothing to do with the luminosity. And the electronic noise and the digitization as well. The DCR noise will increase by the integrated luminosity because we will have more damage to the SiPM, and we will have more DCR noise as a result of this damage. And then the timing resolution as a function of the number of photoelectron also, because in the beginning of the life, we have more number of the photoelectron. By the end of life, we will have less number of the photoelectron, which I'll explain later why. And therefore the timing resolution will be affected by that. And here in the green, you see the sum of all these effects. So the timing resolution as a function of the integrated luminosity from the first time to the integrated luminosity of 4,000 inverse femtobarn will increase from 30 to 65 picosecond. So this timing resolution has been done. I mean, this study has been done in simulation, assuming that the DCR method is assuming the ideal DCR noise cancellation method. So later I will explain later how this cancellation method works to get actually this timing resolution. So going back to this plot, the sigma time is proportional to the inverse of the number of the photoelectron. And also the sigma from the DCR noise is proportional to the noise and is proportional to the inverse of the number of photoelectron. So the number of photoelectron has many contributions. So one of them is dependent on the crystal. So it depends on the energy of the deposited energy from the MIP. So it's very important to choose a crystal that has a very high stopping power, so we can have high amount of energy deposited from the MIP. And also it depends on the light yield of the crystal. So it's very important to choose a crystal that has a very high light yield. And it's also dependent to the inverse of the scintillation decay time. And also is dependent on the light collection efficiency. So this is very much dependent on the crystal coupling to the silicon photomultiplier. So that's why in the previous slide, I explained that there was a huge effort and study how the coupling between the crystal and the SiPM should be to maximize this factor. And also on the photon detection efficiency, which is a characteristic of the silicon photomultiplier. So it's very important to choose a silicon photomultiplier that has high PDE or photon detection efficiency. And the noise is proportional to the square root of the DCR. This relationship has been expected by some simulation study. All right, so let's go back to the description of the LYSO or crystal arrays. So the LYSO actually stands for lutetium, yttrium, orthosilicate crystals that are activated with cerium. In short, we call them LYSO. So these crystals have very excellent radiation tolerance, or are very good for this high radiation environment. They are very dense. The density is more than 7.1 gram per square centimeter. So a MIP can deposit around 4.2 mega electron volt, including the impact of the angle, because they can enter the crystal at different angles. So we will have basically 0.86 mega electron volt per millimeter. And these crystals are very bright. The light yield is around 40,000 photons per MeV. And they have a very fast rise time, around 100 picosecond, and decay time is around 40 nanosecond. So here you see a picture of the LYSO bars, 16 arrays, 16 bars. So as I said, these crystals are very radiation tolerant. So this is a study that has been done to study the light output of the crystals before and after the irradiation, and also the timing resolution that they can get after radiation to full ionization dose, including the safety margin of 1.5. So on the plot on the left, you see the light output. So this is for different crystal vendors. So basically there was actually also an agreement between different vendors. So this is the light output after irradiation. So this is the ratio of the light output before the irradiation and after the irradiation. So as you see, after irradiation, the light output slightly degrades. So instead of getting 1, so the ratio is around 0.9. But its light output relationship on the timing resolution was almost negligible. So the average impact of the radiation on the time resolution was around only 5%. The other study that has been done, it was the characterization of the crystals as a function of the temperature. When we increase the temperature from -30 degrees centigrade to 20, the light output decreases a little bit. But on the other hand, the decay time is going to be faster. And if you remember from the previous slide, the timing resolution is proportional to the light output and is proportional to the inverse of the decay time. So although the light output is going to be decreased, but the decay time is going to be faster. So the timing resolution, after all, is going to be almost constant. So for the crystal, the temperature is not really a big issue. But indeed, for the silicon photomultiplier, it is, which I'm going to explain in the next slides. So the silicon photomultipliers. So silicon photomultipliers are the devices that are very compact and they are very fast. The single photon timing resolution is around 100 picosecond. And they're insensitive to magnetic field. So actually, they are very good if you want to use them in the presence of the magnetic field. And they have a good radiation tolerance. It's I call it good, but it's not perfect because of the rate, because they are not indeed totally radiation hard. They can be damaged and they can produce the dark current. And here you see that the dark current as a function of the neutron flux. And if you increase the neutron flux, you see that the dark current increases a lot. The silicon multipliers, so each pixel is 3 by 3 millimeter, and in each pixel we have 40,000 of microcells. So the size of the microcells can be anything between like 15 micrometer or even 50 micrometer. So if the pixel size are smaller, then the photon detection efficiency is lower. And if the pixel size are bigger, we have higher PDE, but at the same time, we will have higher DCR or less radiation tolerance. So there's a trade-off between the size of the micro channels for having the radiation hard or having also high PDE. So the optimum size is around 50 micrometer. And they have good photon detection efficiency around 20 to 40. And the operation gain along the LHC life can change from 4 to 10 to the 5 for the beginning of life down to 1.5 to 10 to the 5 to control the DCR or dark current rate. So this dark current rate actually is the main challenges that we face when we were developing the ASIC, because it's the main factor basically that it had extra timing resolution, and there was a huge effort to develop an ASIC that can eliminate this and also to actually handle this dark current rate from the SiPM point of view. So there are a few ways. Here also I will tell you how much we expect that this year along the LHC life. So at the beginning of the operation of the LHC, the DCR is very low, of the order of some few megahertz, or almost we consider it as 0. And the number of the photoelectrons is around 9,500 with the SiPM gain of 3.8 to 10 to the 5. And as we go to the end of life, when the integrated luminosity is going to be 3,000 inverse 1 to 1, the DCR rate is going to be up to 55 gigahertz. And the number of the photoelectron is going to be 6,000 photoelectron. So the number of the photoelectron decreases and the DCR rate increases. So it's very important to try to minimize the DCR rate. Otherwise, the impact on the timing resolution is going to be huge. So there are several ways that we can mitigate the DCR noise. One of them is to lowering the temperature of the SiPMs. So the normal way to lower the temperature of the SiPM, the whole electronic, is by using the CO2 cooling, which we can reduce the temperature to -35. And using that, the DCR can decrease by a factor of 1.8 every 10 degrees. However, later it was clear that this cooling up to -35 is not enough to decrease the DCR up to 55 years for the end of life, which I will explain better in the next slide. There was a need for additional cooling with thermoelectric coolers. And then another way to mitigate this DCR noise is annealing of the SiPM at 15 to 20 during the shutdowns. And so when we do the annealing of the SiPM, we can reduce the DCR, and also it also improved the basically the DCR versus the temperature coefficient, which means that if we do the annealing, the DCR is decreased faster when we lower the temperature. So instead of 1.8 per 10 degrees centigrade, it will be reduced by a factor of 2.1 per 10 degrees centigrade. And another way to control this DCR is by adding a noise cancellation circuit in the front-end ASIC. So now I'm gonna explain to you about this additional cooling with thermoelectric coolers. So the DCR that we expect for the end of life in the TDR, which is 55 gigahertz, was by extrapolation from irradiation so basically they irradiate the SiPM to the flux of 2 to 10 to 12 neutron equivalent per square centimeter, and then they try to extrapolate it to the condition of the end of life, and then they estimated to have a DCR of the level of 55 gigahertz, which affects the timing resolution from 35 picosecond worsening to 65 picosecond. This was the TDR basically estimate forecasting, let's say. So in TDR, we thought, or they thought that the temperature of -30 and annealing of 15 to 20 degrees centigrade, the timing resolution is going to be between 35 for the beginning of life and getting worse to 65 with 4,000 inverse femtobarn integrated luminosity. But at the end, when after irradiation to the full fluence of 2 to 10 to the 14 neutron equivalent per square centimeter, it was shown that the DCR level is going to be much higher. So in this condition, which is a temperature of -35 and annealing of 15 to 20%, indeed, instead of getting this black line, we are going to have this red line. So the timing resolution is going to be worsened to 95 picosecond. So there was a need to have additional cooling. So that's why we introduced this thermoelectric cooler. So these thermoelectric coolers are heavily doped silicons that we place at the back of the SiPM arrays. So here, this is the back of the picture of the back of the SiPM arrays. So this has 16 SiPM pixels. So we place them at the back of the SiPM device. So this device is successfully tested and under the irradiation to the full fluence. And so what can it done is that it can provide additional cooling around 10 degrees. So we can reduce the temperature from -35 to -45. And also it can provide a better annealing also up to 40 to 50. And also the possibility for annealing during the beam operation. So here you see if we cool down the SiPMs to -45 degrees with the help of the TEC, and we made annealing of the SiPM with the temperature up to 40 to 50 degrees centigrade, we can basically recover the sigma time that was expected in the TDC. All right. So now let's going back to the performance of the sensors in the test beam. So this study has been done in 2018 in the very beginning of the project, just as a proof of concept. So the electronic is not really the electronic that is not really the final electronics, but was just a proof of concept. So here on this picture, you see a LYSO crystal bar, and that is being read by 2 SiPMs on both ends. So the LYSO bars have 2 timestamps on both ends. So here is the time of arrival of the signal on one end. So of course, depending on the impact point of the MIP along the crystal bar, the time of arrival is different. So if it's closer to the sensors, it arrives sooner. If it is more far from the sensor, it arrives later. And on the other hand, this is the time of arrival on the other sensors, but the average is constant. So it is independent on the point of interaction. And on the plot on the right, this is the timing resolution on each ends of the bar. And if you combine the 2 timing information, the timing resolution is improved by a factor of square root of 2, and which is around 30 picoseconds. So the timing resolution of the 30 picoseconds for the beginning of life has been achieved. So going back to the readout electronics, which actually LIP is leading this project. So this is the picture of the BTL readout electronics, which consists of the 4 front-end board. Each front-end board has 6 ASICs. This is the ASICs, and each ASIC can read 32 independent channels. So here, so as I explained before, we have these crystal bars that are being read by 2 SiPMs on both ends. So this is the picture of the crystal bars. The SiPMs are here. This is one ASIC, can read 32 channels or 32 SiPM pixels. And the readout electronics ASIC is being called TOFHIR. TOFHIR stands for time of flight high rate. So the requirements for this front end is that So the MIP signals have the number of photoelectrons that we have from the MIP signals from the beginning of life of operation of LHC to the end of life is between 10,000 photoelectrons down to 6,000 photoelectrons. So it should be able to deal with this number of photoelectrons and still provided with high resolution. And these events, the MIP rates is around 2.5 megahits per second per channel. So it should deal with this rate of the events. So, and the timing information, these photoelectrons are distributed in time with Poisson distribution. So it's very important the timing information is the best part of the signal to get the timing information. It's the very beginning of the pulse where the pulse is the fastest. So it's very close to the baseline. So the time is given by the arrival of the first 50 pico photoelectrons. So it should be low noise, or at least it should try to lower the noise to be able to get the timing information by the first 50 photoelectron. And the electronic jitter should be around 20 picoseconds, not more than that. And the charge, so it provides a charge integration on time over the threshold. The accuracy of the amplitude measurement should be less than 5% for time of corrections. And also, more important than all of this, it should be able to cope with the dark counts that is generated by the SiPM due to the radiation damage. So TOFHIR ASIC actually is developed by the Precision Electronics company, which is a startup that is created at LIB and in collaboration with LIB. So there has been since end of 2017 or beginning 2018 that this project has been started. There has been a few versions of the TOFHIR that has been developed. The first version, which we call it TOFHIR 1, was based on the technology which is called UMC 110 nanometer. This technology was not radiation hard. And this ASIC was basically based on the ASIC that was previously developed between Precision Electronics and LIB for the time of flight positron emission tomography. So that was very quick production. It didn't have the DCR cancellation module, and it was not the radiation hard, but it was good enough to test the system. The second version that was, we call it TOFHIR 2, is based on TSMC 130 nanometer. And it's a totally new front-end design. So the front-end was completely redesigned. It was not based on TOFHIR 1. And it has a DCR noise cancellation circuit. So the first version, which we call it TOFHIR 2A, the test started on July 15, 2020, so around 6 months ago. And so far, all the tests are all the tests are so good, which I will explain at the end of this talk. Some results that so far we obtained with this version. And the second version, which we call it TOFHIR 2X, which was submitted in November 2020, has an improved version of the DCR cancellation circuit and has a current mode discriminator. The previous version had the voltage mode discriminator. And then the final version, which we hope it will be the final, it would be TOFHIR 2B, which has basically improved single event offset protection. So the TMR protection, so in the current version also is a radiation hard, and it has a SEU protection, but the protection of the clock tree is not well done. So this problem is being solved in the last version, in the final version. And the MPW submission will be in April 2021. So here on the picture on the right, you see the picture of the TOFHIR 2A chip. So the dimension of the chip is around 8.5 to 5.2 square millimeter. So here you see the picture of the TOFHIR channel, which has a preamplifier. And the post amplifier, it has post amplifier T, which has two discriminator for two timing measurements, and it has the post amplifier E for the energy branch, and it has it has a discriminator. So it gives you two TDC and one KDC, and both of them are sharing a 40 megahertz ADC and has a trigger logic. So again, this chip, so in the pulse amplifier, there is this DCR noise cancellation circuit that in the next slide I will explain more in the details. So this chip is able to cope with the high rate 2.5 megahertz of MIP and plus 1.5 megahertz of the low energy hits per channel. And also is being able to handle the variation in dynamic range. So as I said, we have more number of the photoelectron in the beginning of life and less number of the photoelectron for the end of life. And the power budget is around 15 megawatt per channel. So the DCR noise cancellation that is basically implemented in the pulse amplifier. So the concept of this circuit is simple, although the implementation was not that simple. So basically, it gets this is the input signal. It gets the input signal, it delays it and inverts it, and it adds it to the input signal. And this is what we get at the end. So as you see, the input signal is around, the width of the input signal is around 300 nanosecond. But the width of the output current after delaying and the subtraction from the input signal is around 25 nanosecond. So here, using that, basically now we cut down the noises, and also these short output pulses, it reduces the pileup between the consecutive events that are coming every 25 nanoseconds. Also in this plot, this is an example of the events that are coming randomly but in a realistic case of the LHC. So the red curves is the input signal if there is no DCR noise cancellation module. So you have here a big events, you don't have any events, here are the big events and the smaller events. And as you see, since these pulses are pretty wide, there is a large pileup between the consecutive events. But the black curves are basically the output signal that you get after the DCR noise cancellation module. And as you see, the pulses are much narrower, and there's the level of the pileup between the events are basically almost zero. And here, there has been a study on the effect of this DCR noise cancellation module to see how much gain we will have on the timing resolution from the signal that is generated at the SiPM to the signal that is generated at the output of the DCR noise cancellation module. So in the ASIC, the sigma time or the timing resolution is defined with a simple rule of thumb, which is the sigma noise over the slew rate of the pulse. So if you look at the slew rate of the signal that is generated at the output of the silicon photomultiplier is around 135 amp per millisecond. And the slew rate of the pulse at the output of the DCR module is much lower, is 9.93. So which is not good for the timing resolution. But what matters is the ratio of the sigma noise over the slew rate. So the noise RMS at the output of silicon photomultiplier is 2.45 to 10 to the minus 5, while the noise at the output of the DCR noise cancellation module is around 5.12 to 10 to the minus 7, so 50 times lower. And so what defines the timing resolution ratio between them? So that the timing resolution estimated by the sigma noise over the slew rate at the output of silicon photomultiplier is going to be 180 picosecond, and at the output of the DCR noise cancellation module is going to be 52. So you see that the timing resolution can be improved with this method by a factor of 3.5. And this study has been done for the condition of the end of life, which has a DCR count rate of 55 gigahertz, double readout LYSO cores, and the MIP signal with 6,000 photoelectron, and the SiPM gain of 1.5 to 10 to the 5. So now that I explained the TOFHIR readout electronics, I give some results that we get with these TOFHIR ASICs. So first, I explained the results that we obtained with TOFHIR 1 in 2019. So the TOFHIR 1, as I said, it was not radiation hard. It didn't have the noise cancellation module, and so it was not really perfect for timing, especially in the presence of the radiation. But it was a very quick production based on another version of the chip that we developed for the positron emission tomography. But what this chip does, what the main goal of using this chip was to do a BTL system test to do the integration and the readout test of the BTL system So to see if in the presence of all, so to validate the full acquisition chain and assess the impact of the system noise in the time resolution. So the TOFHIR ASIC was mounted on the front-end board and was read with the front-end boards through the concentration card. So as I said, each readout, as I explained before, each readout unit has 4 front-end boards, and all these front-end boards are being read through the concentration card and powered through the power converter boards. And the data acquisition was through the prototype DAC system that is going to be used in the final BTL system. So here you see the picture of the readout unit prototype 1. So we have 4 front-end board. This is 1, 2, 3, and the 4th. All of these are being read together with the concentration card and get the power through the power converter boards. And the voltage of the silicon photomultipliers are provided through ALDO boards. So this is here, you see the picture of the experimental setup that we had at CERN. So again, here you see 1 front-end board. This is, you see another board, not the final board, not the concentration board. And here you see the front-end board connected to the concentration card. So here in this first setup, the front-end board is connected to another front-end board called front-end board type D that was developed for the at LEAP for the readout of the electronics for the positron emission tomography. That was well validated and is working fine. But at the end, what is being used in the BTL is a concentration card. So the idea was to get the results with the FEBD and compare the results with the concentration card to make sure the full chain in the presence of the concentration card is working properly, and the readout DAC unit. On each front-end board, we have 6 ASIC, and each ASIC can read 32 channels. So we connect a SiPM array of 4x4 channels to the ASICs. So then, and we look at the timing resolution between 2 channels of the SiPMs. So this is a summary of the, and we look at the coincidence timing resolution to remove the correlated noise. So this is a summary of the results that we obtained. So in the very first test, we look at the timing resolution between 2 channels of the SiPM that are being connected to the same ASIC on 1 front-end board. And we look at the results when the front-end board was connected to this FEBD board, which is not the final board that is going to read the front-end board. And we also did a similar measurements when the front-end board was connected to the CC, which is being used in the BTL readout units. And as you see, the sigma time or the coincidence timing resolution as a function of the TOT in the case of using the FEBD or the CC are the same. And here, the TOT of the 90 picosecond is with the laser pulses is similar to the slew rate of the LYSO pulse. Sorry, I forgot to mention that here we excite the SiPMs with the laser pulses, not with the lights from the LYSO, but with laser. And then we tune these lasers to get a slew rate that is similar to the slew rate of the LYSO pulses. So the laser pulse that gives similar slew rate to LYSO pulse has a TOT or time over the threshold of around 90 picosecond. So here it was confirmed that the CC is working properly because the results we got with the CC was similar to the result that we get from the FEBD. And in another test, we used against same channels in 1 ASIC, while 1 front-end board was connected, and another time while 2 front-end board was connected, and in another measurements while 3 front-end board connected, and in another measurement while 4 front-end board was connected. It was meant to see if by adding more front-end board connected to the CC card, we add more noises to the system or not. And as you see, the results are in agreement. So which means that by adding more front-end board to the CC cards, the result was not deteriorated and there was no external noise in the system. And in the third set of measurement, we look at the timing resolution between different channels of the ASICs, in different ASICs, not in 1 ASICs. And again, the results was in agreement with the results that we get between the timing resolution between two channels of the same ASICs. And in the final measurements, we look at the pair, we pick up a pair of channels in different ASIC on different front-end boards, not in the same front-end boards. And again, there was a little degradation in the timing resolution, but in all these studies, the timing resolution that we obtained was around 30 to 40 picosecond. And 30 to 40 picosecond constant timing resolution can be translated to 28 picosecond on the channel timing resolution or timing resolution per channel by dividing this by square root of 2. And when we have the LYSO bars with two SiPM being read by and two ends with two SiPMs, this again, we gain another factor of square root of 2, which we get 20 picosecond on the bar resolution. So adding photostatistics to this, because this was with the laser pulses, which has the stored as a LYSO, but excluding the photostatistics, we will get the promised timing resolution for the beginning of life, which is around 35 picosecond. So the purpose of this study with this version 1 of the TOFHIR was to see the system noise doesn't deteriorate the intrinsic performance of the TOFHIR, which indeed was proven. And now going back to the performance that we expect with TOFHIR version 2, which has a DCR noise cancellation module. So we expect to have a timing resolution that of the order of maximum 65 for the end of life, where we have the 55 gigahertz DCR. So this is a study that has been done in simulation with TOFHIR 2A and TOFHIR 2X. So in simulation this simulation that has been done with the Cadence tool is a tool that we basically use to develop or design the electronics. So it's very realistic. So the LYSO with photostatistics are simulated. So the number of the photoelectron is defined for different conditions of the LHC, for the beginning of life where we have 9,000 photoelectron up to the end of life where we have 6,000 photoelectron. So in the simulation, the gain of the SiPM is also defined according to reality, so which is 3.8 to 10 to the 5 for the beginning of life and down to 1 to 5 to 10 to the 5 for the end of life. And the DCR also is simulated, so the events are coming with different rates at different stage of the LHC life from 0 to 55 gigahertz. The SiPM jitter is also defined in the simulation, which is 100 picosecond. The TDC digitization added to the timing resolution, which is 20 picosecond, and the SiPM crosstalk is also included in the simulation. So it's a very realistic way of simulating and assessing the timing resolution for different during the LHC life. So with TOFHIR 2A, which has a BTL noise cancellation module, but it was not optimized, we estimated to have around 30 picosecond for the beginning of life. This is for double readout LYSO bars. And we estimated to have around 90 picosecond for the end of life. In TOFHIR 2X, that has the improved version of the DCR noise cancellation module and the discriminator was in current mode, we managed to improve the timing resolution for the end of life from 90 to 65 picoseconds. So we gained 25 picoseconds. And for the beginning of life is around also 25 picoseconds. So this version, which is TOFHIR 2A, we already received it and started testing it since July. But TOFHIR 2X only submitted for fabrication in November and we haven't yet received it. So this version that we received it, we tested it almost in the last 6 months and we have some results which I'm gonna present in the next slide. So this is some experimental study of this TOFHIR 2A. Again, all this study that has been done in Lisbon are with the laser because we don't have, I mean, we have crystals, but we don't have a high energy beams. So therefore, the real study with the LYSO and the beams with the 4 MeV energy deposition can be only done in the test beams. So all the studies are being done with the laser, and we try to tune the laser to get a slew rate that is similar to the slew rate of the LYSO. So this study has been done with the HDR2 SiPM, which is the version of the SiPM that is going to be used for the BTL with a gain of 3.8 to the 10⁵, which is the gain of the beginning of life. So the laser, with the help of the attenuator, has been tuned to give us different amplitude at the output of the discriminator. So the red one is the timing resolution per channel that we obtain as a function of the amplitude of the laser. And the red one is the timing resolution that was estimated in simulation with a similar condition, with a similar laser pulse that was simulated with the beam width similar to the measurements and with a similar amplitude that we get at the output of the discriminator. And as you see, there's a very good agreement between the simulation and the measurements. The laser amplitude that gives similar slew rate to the MIP for the beginning of life is around here, which gives the timing resolution of around 22 picosecond. Adding photostatistics on top of that is the timing resolution that we expect to have from the simulation, which is around 35. Another study has been done to estimate the timing resolution in the presence of the DCR, or dark current noise. The dark current noise has been emulated with the help of the LED. So LED is calibrated to give the SiPM current equivalent to the current that the DCR will give us at different levels or different frequencies. Again, this study also has been done with the SiPM gain of 3.8 to the 10⁵ with two laser intensities, one of them around 40 millivolt pulse amplitude, another one with 160 millivolt pulse amplitude. Again, here, the red curve is what you get from the simulation. So it's the laser with an amplitude of 40 millivolts superimposed with 0 DCR rate, superimposed with 5 gigahertz DCR, and superimposed with 20 gigahertz. And as you see, there's a very good agreement between simulation and the measurements. And another study has been done with the higher laser amplitude, again with 3 levels of the DCR. And again, you see that there's a very good agreement between the simulation and the measurements. So this study only has been done up to 20 gigahertz because in LYSO we don't have enough facilities to cool down the SiPM in the presence of the DCR. So when we increase the noise with the help of the LED, when we increase the LED voltage to emulate like 50 gigahertz DCR, the temperature of the SiPM increase a lot, and we don't have enough means to cool down the SiPM. So this study has been done later at CERN, which is actually being now going, where they have a better cooling system and better means of controlling this issue. And the last things that so far that we did with TOFHIR 2A that we have it is the radiation test of the TOFHIR 2A. We did some radiation tests with the X-ray irradiation facility at CERN. So maximum radiation dose that we expect in BTL is around 2.9 megarad. But however, in the X-ray irradiation facility at CERN, we irradiate ASIC up to 7 megarad. And we didn't see any sizable effect up to 7 megarad on the front-end amplifier TDC and KDC, which was very good. So including the safety margin, the ASIC is working properly in this irradiation environment. And the other test that has been done was with a heavy ion facility at Louvain-la-Neuve. So there is a facility to test the response of the electronics component to the single event effect. So ASIC was irradiated with different ions covering a wide range of LET and ranges. And we validate that the TMR or cheaper modular redundancy in the configuration register is operating as expected. So just as a brief explanation of what TMR is, so the configuration bits are triplicated, which means that we have 3 copies of the configuration. So if because of the irradiation there is any flipping in any configuration, since we have more copies, they can be recovered. So in the presence of the many ions with the range of LETs, we basically prove that this TMR on the configuration register is working as expected. We are coming to an end. So as I explained, the Large Hadron Collider will undergo a high luminosity upgrade. So we will have 10 times more integrated luminosity, which translates to 5 times higher vertex density, or we will have 5 times more pileup interaction. So this is a very challenging environment. So we need to be able to reconstruct the events in this high pileup environment. So the CMS phase 2 upgrade will have the MIP timing detector that can tag the events with a precision of 30 to 60 picoseconds to mitigate this pileup condition of the HL-LHC. And we'll expand the CMS LHC physics reach. This is so LIB is leading the development of the BTL readout electronics. And the BTL and the ETL are rapidly progressing toward the engineering solution. So almost all the challenges to achieve the TDR performance have been addressed in both cases. And that's it. Thank you for attention. And if you have any questions, I will be happy to answer.
Yeah, thank you very much. It was very interesting to see all these amazing improvements. Any question? Please raise your hand or directly speak.
I had a couple of just simple curiosity-led questions. So you mentioned that they're all lateral to your studies, I'm afraid, but I was really impressed with your results. But at some point you mentioned that there were studies to check what the best coupling was between the LYSO and the SiPMs. Mm-hmm. And what was it in the end? What are you going for?
I mean, after all, it's a glue. But the type of the glue that they used, they did several studies to see what type of glue that they have to use. And
okay.
Yeah, basically it was on the property of the glue indeed.
I was mainly curious because the glue has some chance of degrading over the years with the radiation dose, and that was really what was behind my question.
Right. So I mean, the details of the properties of the glue actually is not in my knowledge.
No, sure.
But as far as I know, it's gonna be glue, but maybe a glue that doesn't change the properties.
Sure. And then I had a different question, which was I hadn't realized that you have two different front-end chips for the ETL and the BTL. Mm-hmm. What's the difference? You know, I see that the TOFHIR is really being targeted to the SiPMs, but is that right?
Right. So between the BTL and the ETL, for the BTL and the ETL, we use two technologies. So for the barrel timing layer, we use silicon photomultipliers and the crystal bars. And for the ETL, we use other technology, which is this L-gas. So, and the reason is that, so the ETL is exposed to 10 times higher irradiation. So it has to be really radiation hard. That's why they use these L-gas sensors, because it's totally irradiation hard. But the problem is that, so, I mean, it was maybe optimal to also make the BTL with this technology. But the price of the L-gas for that, because BTL is much higher than the ETL, and if you want to make the BTL with L-gas technology, the price is going to be huge and it's not affordable. Mm-hmm. So that's why we use another technology for the BTL. But then we have this also radiation problem with the SiPM, but then we had to deal with it, and then we had all these challenges to make the circuits to handle this high VCR level. But after all, it was successful.
Okay, so there's no big difference in like the charge of the integrated charge of the signal for L-GAD and SiPM, or is there some big difference like that?
No, in that case, after all, we managed to get a similar performance between these two, to get a timing resolution of the order of 30 to 35 to 45 with the L-GAD, and the 35 to 65 with the BTL, mm-hmm. and the charging integration and the charging information with the uncertainty of 5% in both of them. But as I said again, the reason that we used two technologies was just the cost.
Okay. Well, thank you.
Thank you. Pedro?
Hello, Tahereh. Thank you very much for this very nice presentation. I'm sorry if my question seems silly, but what happens if 2 or more particles or 3 particles traverse the same LYSO crystal? I imagine the probability must be very low, but still, is it coped with? I mean, you would not know the position of the particle inside the crystal. You probably could know that there are more than one particle because you get a strong signal. But also the other question was, given that the signal is after all larger, and you just want the first raising of the signal, what happens if a particle traverses the crystal while the signal of the previous particle is still not yet produced, collected? Would you be able to get a second rise up, for example?
So first of all, if 2 particles arrive at the same time in the crystal, then we consider as one, so we cannot distinguish them. Your second question is that if the particles, arrive consequently, but one of them is still, the other one arrives on top of the falling edge of the previous one. So what happens is that, as I said, the signal that we get with 1 particle is around 300 nanoseconds, which is very wide. So and events are coming every 25 nanoseconds. So it's very common for the next signal to appear on the falling edge of the previous one. But what the circuit does is that it shrinks the width of the signal from 300 nanoseconds to 25. So the probability for the 2 consecutive events to appear right on top of each other is much lower. So,
yes, but this shrinkage happens on the electronics, right? Not in the collection of the signal.
Right.
So in the end, you would get signal collected.
I know, exactly. Still in the beginning, there is still some level of pileup.
Okay.
But after these subtractions of the, after this noise cancellation, which also has an impact on the shape of the signal, although there would be some amplitude reduction of the pulse when there is a pileup. This is correct. But this study has been done in simulation, but it's still, although there would be the amplitude of the signal would be affected, but still we can identify the signals. And then this amplitude reduction with the time walk correction, we can recover the timing information lost due to this amplitude reduction because of the pileup.
Okay, thank you very much.
You're welcome.
Thank you again. Any other comments or questions? Okay, doesn't seem so. Then thank you again, Hel. And yeah, thank you everyone, and talk to you next week then. Thanks.
Bye-bye.
Thanks, bye-bye.